Welcome to qnawire.
This is kind of an interesting problem, kind of a somewhat difficult problem. So I kind of read through it here. So when we have an object rolling without slipping, the rolling friction force is much less than the friction force when the object is sliding, right? Because there's really no relative motion here, because we're assuming that this point down here when rolling without slipping is stationary. So there's really no relative motion. So they say a silver dollar will roll on its edge much farther than it will slide on a flat surface, which we can, you know, um, just observe fairly readily. When an object is rolling without slipping on a horizontal surface, we can approximate the friction force to be zero. Again, that's because there's basically no relative motion between what's rolling and the surface. So that the um, that the accelerations are approximately zero, and that the velocities, so the acceleration and the angular acceleration are about zero. So this is close to zero. So if we're just rolling without slipping with no other, with not accelerating, not just rolling at a constant velocity, um, and that the velocity and the angular velocity are approximately constant. So that then rolling without slipping means that the velocity equals r times the angular velocity, and the acceleration equals r times the angular acceleration. So that means, again, that's basically assuming that this point is stationary. This point here is instantaneously is not moving. So we said if an object is set in motion on a surface without these equalities, sliding friction will act on the object as it slips along until this rolling without slipping is established. So what we have here is we have a cylinder, okay, with a mass capital M and with a radius capital R, that's rotating with an angular speed of omega naught. So it's basically spinning here. No friction force. It's just kind of spinning there. Kind of like say you have a like a tire spinning, right? That it's just spinning freely, slipping on the pavement. Um, so its angular velocity is omega naught about an axis to the center. It's set on a horizontal surface for which the kinetic coefficient is mu k. So now we have this thing spinning, but it's set on a surface, but we have some friction here. So we don't have no friction here, but we have a little bit of friction. And the direction of this friction force is kind of going to change as we go through this problem. But I just drew it to the right as positive for now. So what we have then, so basically we have this thing spinning, and we set it down on something, and it kind of spins, and it moves because there's friction here. But it's still slipping. But then all of a sudden it gets up to a speed such that this point here has a zero velocity, which means that it all of a sudden starts rolling without slipping. Because basically it's the static coefficient of friction then that comes into play for that case, which is going to be greater. So we have the normal force equals the mass times gravity. We have the friction force is the static coefficient of friction, or the kinetic coefficient of friction times the weight, or the normal force. Okay, so again we have slipping here, so that's the kinetic. That means that the only force here is the friction force, and so that has to be the mass times the acceleration, and that gives us that A equals mu k times g. So that's when we set this thing down spinning, it starts to accelerate, and that acceleration is the kinetic coefficient of friction times gravity. Now, if we do a moment balance on here, we get that minus the friction force times r equals the mass moment about the center of mass here, which is 1/2 mr squared, times the angular acceleration. Now, Let's see here. The friction force, we know, is this value here, which tells us the angular acceleration is, let's see here, I think I missed a sign in here. Yeah, I did. Well, yeah, I missed this sign. This should be plus. This should be plus. That's what I did. Yeah. So I basically changed the signs on this one from my notes, and I didn't copy everything down. So again, obviously, clearly, alpha is minus 2 mu k g over r. So we have some angular acceleration, but it's actually in this direction, right? Because this force is in the opposite, is in this direction here. So it's basically saying that it's acting to slow things down, right? Because if it's spinning this way and we start having a force on it this way, it's going to act to slow things down, right? Now, the final velocity when we start rolling without slipping is, we have an acceleration here, and then we have some time. So after some time, we don't know what this is yet, we start rolling without slipping. And then we also know that when we start rolling without slipping, that velocity is going to be r omega. And we know omega is going to be omega naught plus alpha t. But it's going to be slower because alpha is negative. It's going to slow down, right? This is going to slow down, but then it's going to some of that energy is going to go into causing it to move forward. So that says that the time that it takes, again, assuming that these are constant accelerations, the time that it takes is omega naught times r all over a plus alpha times a all over a, and again this is a minus sign in here. Yeah, that's a minus sign. So let's see here. We have solving for t, we get, what did we have there? Yeah, so a minus r alpha. Yeah, there we go. Now, we can plug things in. So we can plug a in, we can plug alpha in, and then we get, after we simplify, we get t equals omega naught r over 3 mu kg. So this is the time it takes to go from, when it's spinning and slipping to then when it starts to roll without slipping. So it slows down enough, the angular velocity slows down enough, and the angular speed and the linear velocity grows enough so that now we have rolling without slipping. And from that point on, like I said, it should roll without slipping because mu static is what's creating, is creating the friction with rolling without slipping, and that's going to be greater than mu kinetic. All right, so they ask us how far will it go? Well, we know that it has, the distance that it goes is just 1/2 times the acceleration times t squared, because it initially started with 0 linear velocity. We know a from here, and we know t from here, so we can plug everything in, and we get d equals omega naught squared times r squared all over 18 mu k times g. So what can we say about this and this? Say, t goes up as omega naught goes up. So as if it's spinning faster, it's going to take longer to start rolling without slipping, and it's going to go farther before it starts rolling without slipping, which makes sense, as it's spinning faster and faster. As mu k goes down, the time goes up, and so does the distance, because basically it takes longer to translate that rotation because we have a very slippery surface. And in fact, if mu k goes down, if mu k goes to 0, then this goes to infinity, right? Because basically, if mu k is 0, then it's never gonna, it's just gonna sit there and spin, right? Because there's no friction to cause it to, try to accelerate. So it's just gonna sit there and spin, which means that t is gonna go to 0, or t is gonna go to infinity, and d is going to go, let's see here, d is also going to go to infinity. Well, basically, it just basically says it would take an infinite distance because it takes an infinite time. So it's kind of a degenerate case there. But you can make, this makes sense. T goes to infinity if mu k goes to 0. And then basically, this would have to go to infinity, but it's not going to move, so it's never going to get there. So that all makes sense, I think. Obviously, units work out. G comes in here, and because that's just because of how the friction force works here. So that'll make sense. Now they also ask us, let's see here, calculate the work done by the friction force on the cylinder as it moves from where it was set down to where it begins to roll without slipping. So this force is moving, because as this thing starts to move, that force is moving, so it's going to do some work. And how we can figure out what that work is by looking at the change in kinetic energy. So we have our initial kinetic energy. It's 1/2 times J times omega naught squared. And our final kinetic energy, so it was not translating, so just rotational kinetic energy. And by the time it starts to roll without slipping, it has some translational and rotational kinetic energy. Now we see that we have values. We know that V is A times T, so this would be VF. And I call this omega F over here. I probably should have called this omega F. Basically the angular velocity when it starts rolling without slipping. So let's call that omega F. So then we have translational and rotational kinetic energy in that state. Now this thing we know is A times T, and omega F is just VF all over R. And doing some algebra out here, we just get that KF is 3/4 MAT squared, right? Well, if we plug in AT here, right, and then we can add these up. And then, so now we know what A is, and we know what T is, right, from before. We know how long it took to start rolling without slipping, and we know the acceleration it has until that state. Now, we can plug those in, and so we get our final kinetic energy, and after some algebra here, lots of things cancel out, is 1/12 mr squared omega naught squared. Now we can see that we can take the difference in those things, and that's going to be the work that this friction force did. And so we have 1/12 mr squared omega naught squared minus 1/4 mr squared omega naught squared. So that's minus 1/6 mr squared omega naught squared. And it's negative because basically we're doing work on we're doing work on the environment. The disk is doing work on the environment in getting this up to speed. So what you can see here is we've lost energy in going from this initial state where it's just spinning on the surface to where it's rolling without slipping. We've lost some energy, and that energy has gone out into the environment through that friction force, which we would expect, right? Friction, usually, friction basically dissipates energy in our system. So we would expect that we've lost some energy, and we've lost, this amount here. And it depends on the mass, the radius, and the initial angular velocity. So an interesting problem. And again, it comes out, it's not difficult problem actually, but we get interesting results here. And again, you can see how answers come out to be fairly simple. And it's not all that intuitive, basically, what's going on here, because it's kind of hard to think about, to imagine what the system is going through. But the fact that M comes into here, well, that basically comes in because the larger the mass, the larger the friction force is going to be. So it's going to dissipate more energy. Why R squared comes in here? This looks like V squared, right? Like a velocity squared. And so we kind of get, the change with an energy, the initial. This isn't the initial velocity, but it looks like a velocity squared. So we can kind of make some sense, that we get a velocity-like term here.